Welcome to the video that accompanies Chapter 1 of Applied Electromagnetic Field Theory. There'll be a video that accompanies each of the chapters in this textbook, and you can find those videos by clicking on the link on the first page of each chapter. Of course, you probably already clicked on that link to find this video, so I shouldn't need to tell you that. At the start of each chapter, there'll also be two other things on the first page. There'll be a list of the chapter learning objectives. For example, in this chapter, we'll be focusing on vectors and vector arithmetic. Of course, this isn't the main subject of this textbook. That'd be applied electromagnetic field theory, but vectors and vector arithmetic are such valuable tools that we really need to spend about the first two lessons, the first two chapters, talking about those subjects and building up your expertise to make sure that when we really hit the ground that you won't have to think about the tools that you're using. There's also a little introductory historical perspective at the beginning of each chapter, and in this chapter it is the fact that vectors were invented literally for electromagnetic field theory. That shortly after Maxwell came up with his equations in 1865, two other mathematicians and physicists, Gibbs and Heaviside, independently developed the use of vector analysis to be able to work with the new equations that Maxwell had just come up with. So if you hated vectors in earlier classes, you can blame electromagnetic field theory for the fact that they even exist. So you've of course worked a lot with scalars and vectors both throughout your time, and scalars of course are numbers that don't have a direction. This would be something like mass or volume. But vectors, which will be the most important subjects that we'll be talking about in this class, do have both a quantity and a direction, something like a position, a location rather, a velocity, or in our case perhaps the strength of an electric field. Those would all be good examples of things that would be vectors. And we'll be using three-dimensional space in this class, of course, as we do in our real life. And so we'll be able to express each of these vectors in three dimensions. So let's talk a little bit about unit vectors. The only thing that makes a unit vector special is that it has a length or a magnitude of 1. And typically it's also in a useful direction. Very often it would be in the x, y, and z direction, but not always. You can also have unit vectors in any other direction as well. So we could have a vector, for example, that would point due north, or a vector that would point due south or due east, or straight out of the Earth's surface. We can then express a location or a quantity, a vector quantity, as the sum of three of these unit vectors. And so, for example, if I wanted to land a plane, I know exactly where I want to land. And I know how far away I am, north-south, and how far away I am, east-west. And I also know how far above the Earth's surface I am. So those three quantities will help me to identify where I am relative to the desired landing point. Now we'll be able to represent these vectors as a. So this lowercase a will only be used to represent unit vectors in this class. And in print, we'll typically use a bold font to represent vectors, but when we're going to be able to, when we're writing them by hand, we'll have to use a little hat symbol. And so that little hat symbol is going to express the fact that this is a unit vector. We'll never use the hat for anything other than a unit vector which has a length or magnitude of 1. AX, AY, and AZ aren't special. I could have called them BX, BY, and BZ. I've seen other places, other books that use X hat, Y hat, and Z hat, or UX hat, UY hat, and UZ hat. So those would be alternatives to the choices that we've made. Here then you can see an expression or a figure that illustrates how a single vector can be listed as the summation or the superposition, the weighted sum of three other unit vectors. And so we have the red unit vectors AX, AY, and AZ, and then this capital A is going to be in the direction of 2a sub x plus 3a sub y plus 2a sub z. And it may not be apparent from the figure, but it's actually a little bit further out along the y-axis. So it's a little bit further out this way than it is this way or this way. So we can represent any quantity in three-dimensional space as the sum of three of these vectors. So let's do a quick example. I like to fill the examples in as we go, so we'll do this one together. Using rectangular coordinates, what is the vector that points from this location, -1, -2, -3, to +2, +4, +1? So what we're going to need to do is we're going to need to, first of all, I need to turn on my pen. What we're going to need to do is determine what is the x. That's not a good pen. So let's try a somewhat thinner pen. So delta x is going to be the destination minus the origin. So for example, if I wanted to go from Chicago to New York, I would think, what is the location of New York? And then I will subtract the location of Chicago. So it's always the destination minus the source. In this case, that would be 2 minus -1. Got to be careful there. There's two minus signs that cancel each other out, and this becomes 3. So to go from -1 to +2, I have to move +3 units to the right. Delta y then is going to be 4, it's y2 minus y1, which is 4 minus -2, which is 6. And delta z then will be z2 minus z1, which is 1 minus 3, which is -2. And so I now have all three of the deltas, and so I can then create the total vector. I'm going to call it A. Now this is not a unit vector, so I don't use the hat. I'm going to put a little arrow on top of it. It's kind of a lopsided arrow, and this is going to be whatever is the x dimension, so that'll be 3 times A sub x, and because it's written by hand I have to put the little hat, plus 6 A sub y minus 2 A sub z. And so that is the vector that I would have to use to be able to go from -1, -2, 3 up to 2, 4, 1. Now there are lots of other things we can do with vectors as well. One of them is we can use the Pythagorean theorem to calculate the magnitude. And so you just simply take the square of each of the 3 dimensions and then sum them and take the square root. And most interestingly, you can convert any vector into a unit vector by dividing the original vector by its magnitude. And so as you can see in equation 1.2, being able to take the original equation, the original vector, and then determine its magnitude and then divide by the magnitude can allow you to create a unit vector in the location of your interest, or in the direction of your interest. So let's consider that example from the previous page, from example 1.1. Let's see what is going to be the magnitude of A. So the magnitude of A is going to be the square root of 3 squared plus 6 squared plus -2 squared. And it really doesn't matter that it's negative because that'll be squared. This turns out to be the square root of 49, which also turns out to be 7. And then I can calculate what is a unit vector. Lowercase a always represents a unit vector. I'm going to give it a subscript of capital A because this is a unit vector in the direction of the vector capital A, and it gets a hat because it's a unit vector. I guess both the lowercase a and the hat are both indicators of the fact that it is a unit vector. This is going to be capital A divided by the magnitude of capital A. And so this turns out to be 3a sub x plus 6 A sub y minus 2 A sub z divided by 7. And then you could either leave that as a fraction, in which case it would be 3/7 A sub x plus 6/7 A sub y minus 2/7 A sub z, or you could write it out in decimal, 0.428. I'll round them to 3 digits. I'll tend to use 3 significant figures in this class. I guess we could make the assumption that all of the quantities that are provided are precise to 3 significant figures. So there's A sub y plus, or I'm sorry, it'll be minus 0.286 A sub z. And that is a unit vector that is in the same direction that you would have to go to move from between the 2 points that were in the first example. We can also do vector addition and subtraction. To do addition, of course, you would simply add each of the individual components. To do subtraction, you have to be more careful about the order, but it's still just a matter of subtracting the 3 components. And vector addition, interestingly, can follow what we call the Parallelogram Rule, or the Parallelogram Law, where you would simply draw the 2 vectors end to end, or head to tail, and then the resulting vector, regardless of the order, a plus b or b plus a, will still end up in the same location. So I can do some quick vector arithmetic here. I've got a vector a and a vector b. What is a plus b? Well, a plus b is going to be 3 plus 4 times a sub x plus 2 plus 1 times a sub y plus 1 plus 5 times a sub z, which I can write out as 7a sub x plus 3a sub y plus 6a sub z. Forgot that last hat there. And then next we can do the subtraction, which is a minus b equals 3 minus 4 times a sub x plus 2 minus 1 times a sub y plus 1 minus 5 times a sub z, which is 1, it's negative 1 times a sub x plus 1 times a sub y minus 4 times a sub z. Now there are two products that we can calculate from vectors. We can calculate the dot product, which will yield a scalar or just a number, and we can also calculate the cross product, which will yield a vector as well as the quantity. It'll have a direction as well. There are two two equations we can use to calculate the dot product. The first of them is shown in equation 1.5. In this case, you're going to take the magnitude of A times the magnitude of B times the cosine of the angle between them. And as you can see in this figure 1.3, that's effectively taking the magnitude of one vector times the projection of the second vector in the same direction. So if those two vectors line up in exactly the same direction, then their dot product will simply be the magnitude of their products. Correspondingly, if they were perpendicular to each other, the dot product is going to be 0. Now there is a shortcut or another way that you can calculate the dot product, but only if both are in rectangular form. So this only works if both of the vectors are in rectangular form. You just simply take the product of the x components plus the product of the y components plus the product of the z components. So let's calculate the dot product of a dot b using that the original equation, the a times b times the cosine of theta. And I know that I have a vector a. So a is going to be like this, and a is 2a sub x. And then I have b, which is 1a sub x, 1a sub x plus 2a sub y, 1a sub x plus 2a sub y. And the question is, what is the dot product between them? Well, I need to calculate what is the theta between these two angles. So theta is going to be the angle that's here. I can calculate theta actually by figuring out what is this quantity right here. Well, this quantity is 2, and this quantity, the horizontal leg of that right triangle is going to be 1. This, of course, is a right triangle. And so therefore I can say that theta is the arctangent of the opposite divided by the adjacent. And the opposite is 2, the adjacent is 1. And so this becomes the arctangent of 2, which is 63.4 degrees. We could, of course, list that in radians. I'll tend to use degrees unless we have a good reason to use radians instead. And then we can do the full dot product then. A dot B is going to be the magnitude of A times the magnitude of B times the cosine of theta. That's the definition from equation 1.5. And so this turns out to be 2 times the magnitude of b. I have to use the Pythagorean theorem for this one. 2 squared plus 1 squared. There's no z component, so I can just omit that one. And then that's multiplied by the cosine of 63.4 degrees. And this all works out to be 2.00, a suspiciously round number. But we'll see why that is in just a second. Let's go ahead and calculate the dot product the other way. In this case then, the dot product A, and by the way, these better work out to be the same. If they're not, then either I've made a mistake or the theory is wrong. It's the product of the x components plus the product of the y components plus the product of the z components. Okay, so a sub x is going to be 2, and b sub x is going to be 1, and a sub y is going to be 0. There is no y component to the a vector, so this is 0 times 2, and then there is no z component of either of the vectors, So I end up with just 2 times 1, which is just 2. Or if we want to make it look just like the previous one, 2.00. So happily we do see that they give the same exact result, and that's not a surprise, but it's nice to see that it's verified in this case. Interestingly, by combining those two methods, we can actually calculate the angle between the vectors. And so here, for example, you can see that if I know the magnitude of A and if I know the magnitude of B, and if I can find the dot product using the second method, the products of the individual components, then the only thing that's unknown there is theta. So I can actually calculate the angle between two vectors. Even complicated three-dimensional vectors, I can calculate the angle between them. So let's see how we might do that for these two example vectors. I have A dot B, which I'm going to find in the same method that I found right up here. And so I'm going to use the same equation that I did up there. And here this one's going to give me A sub x times B sub x plus A sub y times B sub y plus A sub z times B sub z. And in this case, it gets a bit more complicated. So it's 3 times 4 plus 2 times 1 plus 1 times 5. And that works out to be 19. So I found the dot product. The dot product is 19. I can also calculate the magnitude of A. The magnitude of A is going to be the square root of 3 squared plus 2 squared plus 1 squared. And that works out to be 3.74. The magnitude has to be higher than the largest of the three components. The largest of the three components is 3, and 3.74 is higher than that. So I'm feeling better about that, feeling pretty good about that. The magnitude of B is going to be the square root of 4 squared plus 1 squared plus 5 squared. And this works out to be 6.48. And then I can calculate theta. Theta is the inverse cosine of A dot B, whoops, I don't want to put that quite yet, divided by the magnitude of A times the magnitude of B. And notice that this equation that I've just written here is really just a slightly modified version of the equation from back here, where we saw that you can calculate the dot product. The dot product is A dot B is A times B times the cosine of theta. So I'm just slightly modifying that to be able to calculate theta. And so the inverse cosine in this case, it's the inverse cosine of 19 divided by 3.74 times 6.48. And this works out to be 38.4 degrees. To me, it's pretty remarkable that we can already calculate the angle between those two vectors just by the tools that we've developed so far. Well, the last thing that we want to talk about today is cross products. And cross products, of course, yield a vector, and so that means that we need to calculate both a quantity and a direction, a magnitude and a direction. Well, the magnitude is found by the product of the magnitude of A times the magnitude of B times the sine of the angle between them. Don't get that confused with the cosine, which was in the previous case. And then the direction is found by following the right-hand rule. And if you're left-handed, you might think this is another example of the system trying to keep you down. But remember, you can do the right-hand rule while still writing with your left hand, and the rest of us have to put the pencil down. So we're going to be able to see here that if you put your middle finger and put your index finger in the direction of the first vector, middle finger in the direction of the second vector, then your thumb will point in the direction of the cross product between those two vectors, just like the picture there shows. As with the dot product, there's also a shortcut version because sometimes these are going to get to be pretty complicated. And so this shortcut is very nice because it allows us to take any vector. We don't need to think about what are the directions or what's the sine of theta. We can go straight to calculating the cross product by calculating the determinant. The top row is the 3 unit vectors, the middle row is the 3 components of the first vector, and the bottom row is the 3 components of the second vector. And you might say to yourself, oh, I hate determinants, and I really most especially hate 3 by 3 determinants. But remember, there's a nice shortcut, or maybe you don't know about a nice shortcut. You just either literally or figuratively add a couple of extra rows. So here's extra columns. There's an extra column, which is really just a duplicate. It's just a duplicate of the first column. And this one is a duplicate of the second column. And so then you take the downward leaning diagonals, go to the right. Downward diagonals are positive, upward diagonals are negative. And that will allow you to calculate the determinant with a nice shortcut. Now you can write it out as I've done in equation 1.9 and 1.10. I don't recommend that. I don't think that I could memorize those equations if I wanted to, but I can remember the visual pattern that's shown in figure 1.5. And I'll also show you in just a second that you don't even need to actually literally write those 2 extra columns. So let's consider what is the cross product of these 2 vectors, 3a sub x plus 2a sub y plus 1a sub z, and 4a sub x plus 1a sub y plus 5a sub z. Now we could calculate the theta associated with these 2 as we saw in the previous example, and from there we could calculate the magnitude of a times the magnitude of b times the sine of theta. We could find the magnitude of the cross product, but I can't figure out how to put my fingers in the correct directions to figure out the direction of this cross product. So I'm going to need to use the sort of full method here, and that is that a crossed with b is going to be calculated as a determinant. The top row of that determinant gets the 3 unit vectors. The second row gets the 3 quantities of the first vector. And by the way, in dot products, the order doesn't matter. A dot b is the same as b dot a. But in cross products, it does matter because you'll end up with a negative sign if you reverse the order. So it always needs to be that the first vector goes on the second row and the second vector goes on the last row. Okay, so what I'm going to do now is I'm going to do the 3 positive diagonals. And so one of them is easy. This one is right here. So that's just a sub x times 2 times 5. And then I'm going to do the second diagonal, and I'm going to get to here, and I'm going to run out of space. But I pretend that I'm playing like asteroids or something. I go off the right side and back in the left side, and I pick up the 4 right there. So this becomes plus a sub y times 1 times 4. And then the last one, I go off the right side and I come back in the left side again, and it becomes plus a sub z times 3 times 1. Then I have to do the 3 negative leaning directions, or negative leaning diagonals. So I have this one, which goes off there and then comes down here. So this is minus a sub x times 1 times 1. And then I'm going to have minus a sub y times 3 times 5, minus a sub y times 3 times 5, and then the last one is easy, minus a sub z times 2 times 4. And if you do the arithmetic and you group like terms, you end up with 9 a sub x minus 11 a sub y minus 5 a sub z. Again, a calculation that I could not have done without the ability to use this determinant, and the shortcut version of the determinant calculation made the calculation quite a lot nicer. So that's it for vectors. That's our first video. I just wanted to summarize the things that we've just talked about. We talked a little bit about unit vectors. We talked about how you can calculate the magnitude of a vector. You can then calculate a unit vector in the direction of any other vector. And we calculate dot products in 2 different ways. We use the combination of those 2 ways to find the angle between 2 vectors. And then we determined a couple of ways to calculate the cross product as well.